Hello and welcome to another tutorial about the basics of programming. Today we're going to talk about testing. Testing is a rather important and big topic. We will look at different aspects of testing essentials. We will talk about what tests actually are, especially automated tests, why you should write tests, and why it's important to have them. We will write some simple tests for essential function examples, and I will show you what you need to do to write tests, what kind of rules you need to follow, especially in Golang. So as always, we are going to use this beautiful small language Go, which offers testing support out of the box. First of all, I'm going to switch to the terminal. I got a new folder prepared here. I just call it test basics. Can basically be empty in your case. I just added a markdown file for a little bit of short summary for myself for the tutorial. So just in case you didn't install Golang yet, please make a Google search or something similar. Look onto the official Golang documentation how to install it. I also put a link to the installation instructions in one of my first tutorials. If you want to check these, feel free to do so. Now that we have Golang installed, let's say we need some basic implementation so we can actually test something. That is why I will create a new Go file. I'm just going to call it main.go. It's empty. And then I will switch to my editor, which is VS Code, but of course you can use any editor you like. As you know, probably we have to define a package name. We'll just keep it simple and call it name. And we will import the FMT package for formatted input and output just to check our minimal program. Main is the entry function, and here we can print a test sentence like the famous hello world. Save it, go to the terminal and run go run main.go, and as you can see this works. It's our basic program. Now what our basic project setup is working, we can print hello world. Let's actually write a little function so that we have something to test. We are not going to use anything too complex because we want to focus on the testing basics. But let's say we implement a simple function that calculates a product out of integers. So what we want to do is we want to pass an arbitrary count of factors. So returns the product of all given factors. And just in case no factor at all is passed, 0 is returned. So you could write this for a factor, for a product of two factors like a and b, which are integers, but we want to do that for an arbitrary count of factors. And this is where the operator for variadic parameters comes in handy. And you can use that by writing 3 dots in front of the parameter type. It basically means this is a list of parameters, and the compiler knows you can pass an arbitrary count. So you could pass 0, factors 1, 2, or maybe 100. It's all possible. What you need to know when you have additional parameters is that these need to be located before. So just in case I would have another parameter like Boolean, I cannot add it behind it, then the compiler complains, but I can put it before it. That's totally fine. So these variadic parameters have to be located at the end. But we only need this factor list. So we're going to start with a very simple naive implementation. Let's say we have value 1 and then we iterate over the factors. Let's call this factors and use the range construct, which we can use for list types like slices and arrays. So we can also use it for an arbitrary number of parameters, which is basically just a list. Then we say multiply our intermediate result with the current factor, and that is how you calculate the result. We can return it at the end. Remember, when using the range construct, it gives you 2 return values. The first is the index of the current element and the second is the actual element. Since we're not interested in the index, we don't have any use for it in this case, we can use this underscore character to signal that we don't actually need a real variable for the index. Also, what we can do is, instead of writing result is result times factor, we can write it shorter like this, which is actually a short form. So let's say this is a short form for this. And you can use it with different arithmetic operators. You could also use it with the plus or minus operator. It's just a handy little shortcut. Now, we actually have something that we can test. So let's write a simple test for it. At first, why would we write a test for it? Well, without a test, how would you know that the functionality actually does what you expect? How would you know that it works? Of course, I can just call it a few times in my main function like this and then run the program. Actually, let's try this and see. This is basically then I'm doing manual testing. So let's say I can do this. And we're going to use the formatting that I explained in my earlier tutorials. And just call the function here and pass our parameters. And this is how we would test manually. But it's a little bit tiresome and it has some disadvantages. It would look like this. And so we print our results on the terminal and check manually if these are correct. Now the problem is these tests are not automated. So sure, I can run them manually, but it's quite a lot of effort because I have to repeat the manual procedure every time I make changes. Let's say I make some changes to a complex function. This is not really complex, but I could also make changes here. And now I want to make sure before I use my new version of the program or ship it to the customer that it's still doing what I'm expecting. But what happens quite often in the real world is that functionality breaks by accident because someone made a change and didn't write a test for it. So in order to prevent that, I have to make sure to repeat the manual test just to check that it still works as expected. But this is obviously pretty high effort, and it's not a very smart way to do. So one way that is very common in the software industry is to write automated tests. And one type of automated tests, the smallest form of it that tests on a very fine granular code level, are unit tests. So let's write our first unit test. For testing in Go, you simply create a new file that is called like the original file where the functionality lies that we want to test, but we append underscore test at the end. This is the convention that you should adhere to. I'm going to call it main test.go. Now we can just open this file. We place it in the same package, like the main file. And I'm going to import the Go standard package testing. You can read all about it on the internet. There are all kinds of helpful testing functions in there, and there's a lot of example code, documentation, blogs explaining how to use it, and so on. Now to write an actual test, we create a function that starts with the prefix test and starts with an uppercase. And then you usually write the function that you want to test. So we want to test the product. We use upper camel case here. So this is how I'm going to name it. When we run the tests later, the Go toolchain will detect that this is a test by looking at the naming convention. Now, what we also need is a parameter of type t.testing. Testing.t, large T, uppercase T. And this is a pointer type, so we need this asterisk before it. Now, maybe you don't yet know what pointers are. Don't be too confused about it. It's a concept that I want to explain in a later tutorial. If you're curious, you can search the internet. But for this discussion that we're having here, it's sufficient to know we need to define it as a pointer. At this point, we don't really have to understand what a pointer is, although it is certainly helpful. And of course, my function body in the curly braces. Now inside this, I can write my test code. And usually tests consist of a setup or preparation and the actual code that calls the function under test, and then a verification. So let's say tests have to start with prefix test to get recognized by the Go test tool. We also need a parameter of type testing.t. which offers testing functions, as we're going to see soon. The typical order of instructions is test setup or data preparation, followed by a function call for the functionality to test, followed by a verification step. So it sounds more complicated than it is. Let's illustrate it by looking at the product function example. So instead of manually testing, we want to test it here in an automated fashion. And what we can do is we can just call the function and pass the parameters. So let's say we pass 1, 2, 3 as factors, and we store the result. I'm going to call it result, the variable. And now we can check the result. And you can do that with basic constructs like if and equality checks. So we want to check that it's equal. So what we need to do is, if it's not equal to our expected result, which is obviously 6, then we want to fail the test. And we can do that by calling t.error. And I'm going to use errorf, which is similar to fmt, as printf, for example, or fmt.printf, where I can specify a message pattern like this, and then some variables that are going to be substituted into the message. And this is, in our case, the expected value is 6, and the actual value is the result. So in case the test fails, we're going to see what was expected and where the test failed with which actual value. And in case it is 6, we don't want to do anything. We don't need to fail the test, and the test automatically passes. So let's see how this actually looks like when we run the test. Make sure you saved your files and go to the terminal, where we just call go test, and you don't even need a file name. Strictly speaking, it will just run all tests that it finds in the current folder. So that's why it's important to adhere to the conventions. Name your test files with _test at the end, and your test functions have to start with test and have the testing.t parameter. So when I try to run this, I get this error that there's no Go mod file. If you have seen one of my previous tutorials, or maybe you have a little bit of experience in Go, you know that Go modules are a way of structuring programs, especially larger programs. And the test tool complains that they don't have this module file yet. Well, we can easily create a file by using go mod init and specifying a name for our module. You can basically use whatever you like. I'm going to name it according to my repository at GitHub, so that it's actually matching. Run go mod init. It's going to create a new Go module file. There's not much in it, but it's quite important for dependency management, and it also specifies your module path and your Golang version. So in case other people are using your code, especially when you create more complex, maybe open source programs, they know which dependencies and which Go version and so on they need. Okay, now let's try again to run Go test. And as you can see, it says pass for the whole module. This is a very minimalistic output. What I usually like to do is pass the v flag with -v, which means verbose, and it's going to print a little bit more information, like which test it's actually running and how long it took and if it passed or not. So test product is our test function. You can see it ran quite fast. There's not much time that has passed, and it passed. Everything's good, right? That's how we want it to be. But how does it look like when the test fails? We can easily do that. Let's say now I could change the expectation. So let's say we want that result is 5, which is obviously an error in our case, because we wrote the wrong result. But let's say we did this, because of course you can also make errors while writing test code. So there can be an error in the test code, although the function under test is correct. And then I will get this failure. You can see which test failed in which file. We can also see our message. It's always helpful to have an expressive message that says what was expected and what was the actual value. You can also write different messages, but this is a classic example to write what is expected and what was actually the value. And you can also see where the error occurred. This is also very helpful if you have a lot of code and complex calls. You want to be able to immediately see which part failed. So it's in main test Go line 16. We can see, okay, this is the check the verification step that failed, and that's where we have to look into. Then we're going to see, okay, this is wrong, I need to adapt this. Yeah, so far we only had an error in our test. Let's say we also have an error in our actual code. So I already said that we expect product to return 0 if we don't pass any factor. You can actually read it here in the documentation I added. So we're going to assign it to result. Remember to use the assignment operator. This is declaration plus assignment. Since result is already declared here, this is only an assignment, not a declaration. And now we will check if this is not 0. We want to fail the test with the description expected 0 but got this. So we can check if that works. And as you can see, it does not work because our implementation is not yet correct for that behavior. And now you have a classic example where you have a test that proves that the expectation is not working for our productive code. And now you can look into why that is the case. And when we dig into it, we can see, okay, we start with value 1. Obviously, this will not work if there are no factors. We will not run into the for loop, but we will return the initial value of result, which is 1. So a simple way to fix this is we can check if there are any factors at all that we received. We can use the lang built-in function to check the length of factors, which, as I already explained, is basically just a list. So they can use this length check. And of course, you have to compare it to something. We'll say if the length is 0, okay, there are no factors at all. We want to return 0 as a default value when no factors are passed. And now we can do the check and just run our test. And you can immediately see how powerful it is. I just repeat the test command. I already have my test for verification. I don't need to construct a whole manual test case. Testing this manually would be more effort, especially when you have more complex functions. So I can easily run this test in basically no time at any point. Let's say a colleague or a friend of mine makes some changes to my program, to our program, let's say, and he does some modifications to tune this function. Maybe he wants to make it faster or add some special cases. Then he can add his or her own test cases to test these new special functions. But we can also keep my old test, and by running it, the person can quickly check that everything still works as expected. Otherwise, it may happen that some functionality breaks. Or maybe you have a cat that runs over your keyboard and it actually swaps the factor operator with the plus operator, which will obviously lead to a wrong result, and your test would detect that. So that is the value, or one of the main values, of automated tests. You can verify that your productive code does what you expect, and you can make sure that in case of changes, nothing broke, which is happening more often in reality than you probably guess. Now, tests, of course, are never perfect. As we already saw, the test itself could have an error. So when something fails, it's important to investigate if it's the test that is wrong or if it's the function that is wrong. Both are possible. And if you write new code, it is recommended that you add some tests for it to actually have a check that you can use now and in the future. Let's extend it a little bit. What you usually want to do is to check all major cases in your productive code. So we already covered the case where no factors at all are passed. And this is the check no factor chronic case. So this is an important part of testing to cover the special cases. This is a very simple case, so maybe we add a comment, check very basic product. Now let's say we also want to verify it works with negative numbers. Then we are going to write a call that uses negative numbers. Like this. And that should be 60 times minus 7, which is, if I didn't miscalculate, it should be minus 560. Oh, sorry, no declaration, assignment only. Let's see if it actually works. Go test, of course, the V flag. And now I did a mistake. That's fine. Now I can check if my test is actually correct. And of course this is minus 21 times 10 is minus 210 times 4 is minus 420. Yeah, I did a mistake in my test, so I'm going to fix it. And we verified it's actually what we expect. Okay. Is there something else we can check? We checked a simple case, a case with negative numbers, the no factor corner case. Maybe let's add a case where there's a zero contained. Check with one zero element. The result should be zero, of course. And we're going to put it at the end. And if the result is not zero, we need to fail the test. Let's see if it runs. Yeah, perfect, it runs as expected. So this is pretty much it. When we look at the code, we covered this case. We covered the loop case. And yeah, there's basically not much more we can test. We can actually remove this main function here. But as you probably already noticed, there's quite some repetition in here. So there's some duplicated code. We are repeating these not equals checks, and we are repeating these error messages. And on one hand, it is very good that this is very simple to use. It's not very complicated. Go makes it very easy to write these assertions. On the other hand, it blows up the testing code quite a bit, and we want to have it a little more neat and compact for readability and less typing. So that is not very difficult to fix. We can just, as we are doing with regular production code too, we can write a little helper functions for reducing code duplication. Then we only have to adapt these functions instead of adapting lots and lots of places if we want to, let's say, change the message pattern that we print in case of errors. So I'm going to write a function that is called checkEqual. And we need to pass the testing t-type pointer, the actual value, and the expected value. Both are ints, so I can write the int type at the end. And how this is going to look like, I'm going to illustrate it here. We will just call checkEqual. We pass the testing helper type, what we have as an actual result, which is our result variable, and what we expect is the 6. And then we can actually drop this part. And we're going to use it in the other places too. For minus 420. And 0. So right now it's not doing anything, so it would always pass. But you probably guessed it, we only need to do the same like we did before, but now we only do it in one place. That is the power of code extraction. We can say if actual not equal to expected, then we fail the test and say expected this, but got this. And that's it. Save and see if it works. Yes, it does. Let's see if we actually detect some errors. Let's temporarily deactivate the no factors case. And yes, our test fails. Expected 0 but got 1. So it's actually working. Now there's one little trick that you can apply for making these helper functions a little bit more helpful. So as you can see here, it's stating the line where the verification failed, where error F was called, which is line 32. Of course, this is correct. This is the line where we called it and where it failed, but we can't immediately see where in the test itself it failed. So it is this case, and looking closer at it, but it could also be this, because we are also expecting 0 at the end. And just by reading this message, expected 0 but got 1, we are not quite sure if it's this or this case. It would be really helpful to see when the test fails that this is the actual line in this case. And there's a neat little helping function for that. You can say t.helper, and as always, the documentation is a friend. When you look at the Go package documentation for the testing package, you can read about all kinds of interesting stuff. And there is the helper function on the t-type, which is this one. And it says helper marks the calling function as a test helper function. When printing file and line information, that function will be skipped. Helper may be called simultaneously. Okay. So let's see what it actually does. When I run the test, now I actually get the line number of the calling code, which is 19. And that is incredibly helpful in big complex programs, because you don't have to wander through lots of call chains which are nested like a ladder. You immediately see where the test case failed. Okay, now one more thing about testing with the error function is that it actually runs the whole test. So let's say that both these cases fail. So we're just going to simulate that by making our test wrong. Let's say we actually expect 42 here and at the end. And let's see what happens. You can see that we get two errors now. The one in line 19 and the one in line 27. 19 and 27. So as you can see, it's not immediately aborting after the first error. It's running the other test checks too. And this is by design how error is designed. There are different methods. You can read about them in the documentation on the internet. But one notable difference is t.fatal. Fatal means the test has failed and needs to be aborted because it makes no sense to continue the test. This could be the case when we have some complex state changes that we are going to test. That might still be a little bit too abstract for you, so we're going to illustrate it with a concrete example. First, let's revert this to the correct test, and then we are going to write a productive function for our illustration purposes. Of course, I have to reactivate this corner case handling. The test actually showed that I still had a mistake, but now it's passing. So I want to write a little function with you that is called remove, and what it does is it receives a slice of integers. We're just going to call it slice, and you can pass a target integer, which is an integer, and we're going to search the slice for this integer and remove it from the slice. So we're actually returning a new slice, which is our result type here. And as it's most of the time a good idea to document, we're going to write returns a new slice, or no, let's write returns a new slice where the first occurrence of target has been removed if present. Otherwise, a slice with the same elements is returned. So we need to search the slice for the target and create a new slice where the target is removed. But before we're going to implement that, we're going to write the test, and this is a concept that is called test first or test driven, which can be helpful sometimes. It means you write the test before you implement the actual function. How does it look like? Well, we wrote a basically empty function, and for it to compile, we write the minimal version of it, which is just going to return the input slice, so the compiler is not complaining. Then we go into our test, and we write our first test, like test remove. Again, we have to make sure to use a testing T, and we write a first check. So let's say remove last element. So we have a slice that looks like this. I'm just going to use the inline style. And we want to remove the 0. So I'm going to write remove from slice target int is 0. And we reassign it to the slice variable. And we're going to check that it has been removed. So how can we easily do that? Well, first let's write a very naive implementation. We're just going to iterate the slice using the range expression. And if value equals 0, then it's still in there and we have to fail. So this is really naive, but it's a first starting point. Zero is still present. Okay. And now you run the test to check that it actually fails and your test is doing something valuable. And we can see 0 is still present. Now this test-driven approach has some advantages. One advantage is that I have to think first about what my function actually needs to do. So I'm forced to write my specification, or let's say my expectations first, into a testable, so runnable format. And that can be beneficial depending on the context and your work mode and the project and so on. And now I can add the functionality step by step and use the test as a feedback check. So let's implement the function. I'm going to show you one way of doing this with slices, and that is by reslicing. So we're going to iterate the slice, ignoring the index. Or no, sorry, we're going to need the index. And the element. Or let's call it a value. If value equals target, we have found our integer to remove, and we use reslicing. That is, I already showed you slicing operators in my second tutorial video. Feel free to have a look at it. But we didn't really talk about reslicing there. So reslicing is basically cutting a new view on to the slice by specifying new from and to indexes. We can write the slice and using these brackets, the start and end point. Start point in this case is right from the beginning. Colon separates start from end, and end is index. So if I omit the index before the colon, it means start at the beginning. The colon is a separator, and the second integer means until this index exclusive. So index itself is our target, is not included, it's exclusive because we want to cut it out. Now this only cuts from the beginning until before our target index. So it's not quite sufficient, but we will see that when we run our test. So save and run. And as you can see, it passes. Why does it pass? Well, our test case exactly needs to do this. It cuts until the last element. So it works by accident for this specific case. Let's say we want to remove another element, but this time it's not the last one, but the first, which is 4. So I'm going to remove 4 from the slice and check. I'm just going to copy that for the moment, that it's no longer in there. Actually, the for loop is a bit overkill. What we can do is just check the index. So if slice at index 0 is still 4, then the 4 is still present. And we know we must fail the test. So save and run. And it's even a runtime error panic because I have a more serious issue with my productive code. Index out of range because the slice has a 0 length, so actually there are no elements inside it. And as you probably already know, that leads to such a crash during runtime. So that's a good thing because it's better to find it in a test than when we already ship the code to the customer or something else. And we have to look at our production code. Now, as I already told you, this cuts from the beginning to our target exclusive. So in this case, it cuts from 0 to 0 exclusive, meaning the resulting slice will be empty. What we actually need to do is we need a second cut from slice index plus 1, so after the cutting point, until the end. And this is done by omitting the end index after the colon, which is consistent with the first format. And now we have two slices. We have the first slice until the cutting point and the one after the cutting point until the end of the original slice. And we can append these together by our handy little append built-in function that I've also talked about in previous tutorials. The only thing that we need to do to satisfy the compiler is add 3 dots here. And that basically means convert this to the variadic form. So it's the same as I would list all individual elements one by one. And now we basically glued these parts together. We removed the index location because it's exclusive. And that is one way to remove an element. There is another way which is more efficient, especially for larger slices. But for simple cases, this is sufficient and we're going to use it here. So a simple way of removing an element or removing elements is reslicing. It means that we cut a slice from the beginning and from the cutting point and glue them together. And now let's check our test run. And as you can see, it now passes. Of course, we should add some more tests to make sure it actually works. And we probably want to simplify our assertions first. You can do that by, again, writing or using helper functions. So one way is to write a function. We are going to call it check equal slices. And we get a slice we're going to call actual and expected, both in slices. Then the first thing that we want to do is check if they have equal length. because if the length differs, we already know that there is an error. Or actually, let's print the slices themselves. It's probably more useful. Expected slice this, but got slice this. Okay. And once we know both lengths are equal, we still need to check that the values at the specific indexes match. So we can do that with a simple indexed for loop. We know both have the same length, so it doesn't really matter which one we check for length. And we can say if actual at index is not equal to expected, we fail our test. We can actually use the same message. Now let's see if this works as we might expect. We define a new variable, expected, where we store our expectation. That looks similar, but without the 0 element at the end. Take care to pass the slices in the right order, because otherwise the error message might be confusing when actual and expected are swapped by accident. And then we are going to do the same here. We are removing the 4, so only these 2 minus 3, 8 shall remain. And we can remove the rest of the code. Again, this is only an assignment. Let's see what happens. It passes, wonderful. So let's imagine that we add another test and we want to remove the element in the middle. Which is minus 3. And it works beautifully. Now to illustrate something, I want to reintroduce our first version where there was a mistake in case we did not just cut the last element. So let's say we still have this primitive version where we only cut until the target point. Obviously our test will fail now. And what you can see is the first error message and the second. So let's actually set this helper so we get the right numbers. As you can see, this is helpful. And it's failing at 48 and 53. So 48 is this, 53 is this. Okay. Now this is correct that our test detects that, but as you probably already guessed, the whole test builds on the assumption that we make the test slice smaller and smaller. So we're working on this initial slice and we're removing elements one after the other. So the next check builds upon the result of the previous one. Therefore, it doesn't really make sense to run further checks when the previous check already failed. So of course, if we were not able to remove the 4 here, then it doesn't really make sense to try to remove the -3 because the 4 is still in there, and so it will definitely fail. Sometimes that is helpful to not have too much output, or maybe the tests are really long running and take some time and you don't want to continue running, then they already failed, you want fast feedback. That is where the fatal functions come in. So we do that by writing fatal, and there's a fatal F for formatted output with patterns. Let's replace this and check what happens. As you can see, now we only get the first error, and the test immediately aborts, which makes sense in this case because it all builds on top of each other. So that is what I wanted to show you about the difference between fatal and error. So error methods are helpful for failing a test but continuing the test function. Fatal methods are helpful for failing a test when it makes no sense to continue the test function due to results that may be built on each other. Yeah, so that is definitely helpful in some cases. Okay, looking at what we already discussed, it is quite a lot. We can talk a bit about the equal check of slices. And maybe you wondered why we can't just write if slice not equal to expected and then fail the test. That is because the compiler doesn't know how to do this comparison. It cannot compare slices out of the box. It can do with arrays, assuming they have the same type and the same length, because the length is part of the type, but not with slices. So one simple way to solve this is to just write your own comparison function. As you can see, it's quite simple. You do it once for your project and that's it. Another option is you can use a little trick. You can use the reflection package. It's called reflect, and it has some complex meta functionality. So reflection is for inspecting code from the code. You don't have to wonder too much about it, but there is a functionality that is called DeepEqual, and you can call it like this, and it can compare all kind of types for deep equality. It basically works in a recursive way. So if you pass slices, it will compare their elements at the positions and their length. It can also compare maps, structs, and other types. So it's quite mighty. And we can use that to our advantage. So we could write slice and expected and then fail the test like in the usual way. DeepEqual expected slice this, but got this. And this we can deactivate it for a moment, run the test. And as you can see, it is succeeding. Of course, I need to negate this with the exclamation mark because we want to fail if it's not equal. But this was a nice test for the test. So line 54 is still failing, which is because I did not revert our simple implementation here. So again, the test saved me from forgetting to adapting that. Now it works, as you can see. Now, should you use this DeepEqual? It is certainly helpful for tests, so I would recommend it for testing. You don't need to write your own comparison in this case. In production code, I would consider doing something different and implementing it yourself, because DeepEqual is quite complex inside. That is also why it's more expensive. It takes more time if you do that a lot in very computing intensive, heavy request scenarios. Or you could look and search the internet for helpful libraries, but given that it's so easy to write a comparison function, you can easily do that yourself. And since we already did that, we're going to revert it, and I will just note here that for simplicity we can also use reflect.DeepEqual to compare slices, but there is no built-in equality check for slices in Golang. It has probably been a deliberate decision for simplicity reasons. So, final check. Let's see if our test still works when we save it. And yeah, it runs fine. So this is pretty much all I wanted to cover with you for the basics. There's more about testing in general and also testing in Golang. Feel free to do your own extended research, tinker with it, and read about it if you're interested. I would really encourage you to start writing tests and make writing unit tests part of your usual programming routine, because it is de facto standard in the industry. So if you're working in the software development industry, or if you intend on working there, even if it's just a hobby project, or if it's maybe making first steps in an open source project, it is definitely a good investment. In the beginning, it might feel a little bit tedious and that you're spending a lot of time on writing tests. That is true. That is the case, definitely. Even professionals spend a lot of time writing tests, sometimes more time than the actual production code, but it is something that will pay off over time, and more often sooner than you think. Because once you find these errors before shipping to production, and once you realize the power of these simple regression tests, so making sure that you did not break anything when you changed somebody else's code or your own code that you haven't worked with for a while, you will realize the power of automated testing. So that is it about the basics. There's more to it. As I said, testing itself is a field and an art sometimes for itself. There are more things we can talk about in the future, like advanced testing functions, benchmarking, how to make complicated tests simpler, and so on. But this is the gist of it and should get you started in writing your own tests. Look up in the documentation, look what's out there to improve your skills and start writing some tests. If you have any questions, feel free to write them in the comments, and I will do my best to help you out. See you soon.